I'm going to talk about control flow. This is a kind of a map of where we're going. I'm going to simplify it. I break control flow up into three main categories: sequential, non-sequential, and an envelope, or what we call multitasking these days. Sequential is where one action happens after another. Non-sequential control flow is where actions happen in an order that is different from one after another. Envelope is kind of a non-sequential programming, but I think of it as being higher level than non-sequential. Non-sequential breaks down into four main cases: case, call, go to, try, throw, and catch. Call includes recursion and return. Some would say that recursion is in fact a kind of or is the uber parent of calling. And so I'll try to do that if I can here. There we go. Go-to is the main way to change control flow in a standard program. Go-to is not a problem, but unrestricted use of go-to is a problem. Very early on, we realized that doing go-tos all over the place was a bad idea. We invented something called structured programming, and that broke down into if, then, else, for, and while. And then a language called concurrent Euclid used something called a loop, which subsumed both for and while into one construct called a loop, exit, when, and end. It might be noted that first-class functions are really just a kind of go-to, which is even more unrestricted than the original go-to that we had. Continuation passing style comes from first-class functions, and it is just the ultimate go-to that is available to us. Stop treating go-to as something to be shunned and as a useful but very low-level operation. There are different ways to constrain go-tos than just using structured programming. One is state machines. Another one we'll see later is just using an envelope. State machines are interesting. In 1986, Harold wrote a paper called about state charts. I discuss state charts in my blog at this address here. Try, throw, and catch is a bag added onto the side of common programming languages to handle non-sequential dynamic control flow chains. Coroutines, albeit useful, have been left in the dust by most of our current programming languages. Now we'll look at the thing that I call an envelope, which breaks down into processes that are threads and networks. Looking at processes, we notice that they involve shared memory. They use a global variable called the stack, and they involve time sharing. All of these issues are issues based on early forms of computing. Back in the 1950s, CPUs and memory were expensive. These things have given us accidental complexities. Now let's look at networks. This is the wave of the future of computing, in my mind. Networks break down into HTTP and Ethernet, mostly. In networks, we also can draw sensible diagrams of things. Networking has created a new breed of language. We call that language HTML. It is declarative, and it's not stack-based, so it can go across distributed processors. There are parts of HTML that we haven't figured out how to make declarative, so we use JavaScript and other things to help us create more interesting programs using HTML. Up to now, we've been trying to shoehorn everything into a calculator style of programming, embodied by the original use of computers, which was to perform ballistic calculations. A new form of computing, or a different form of computing, is is a distributed control flow or machine control, which tends to break the types of things we can do with current programming languages. Distributed processing and distributed control is going to be where IoT ends up, in Internet of Things. Right now we're using old-fashioned techniques like dropping this enormous library called Linux on top of small processors, when we could be shaving these programs to suit their purpose. For example, controlling a refrigerator does not require all of Linux.